Okay, so we just computed an integral to give us the volume of a volume of revolution. And the way we did it was by chopping parallel to the axis. There's another approach, which is to chop perpendicular to the axis. So now we're going to produce a seemingly different integral that, of course, would have to give us the same answer because we're computing the volume of the same solid. Okay, so here's exactly the same situation. And now instead of chopping vertically, we're going to chop horizontally. We're going to chop into very thin rectangles that lie horizontally, and we're going to follow the same approach as before. We're going to chop this region roughly into rectangles. We're going to compute the volume that each of these rectangles produces when you rotate it around this axis x equals -2. Then we're going to add them up and get an approximation. Take the limit as n goes to infinity, and that's going to give us an integral because it's going to be the limit of a Riemann sum. Okay, so let's look at this. So if we're chopping this region up into these horizontal rectangles, what we're really doing is chopping the interval from y equals 1 to y equals 2. So here is y equals 1 to y equals 2. I'm going to draw it vertically because that's normally how we think of y. So first point we're going to call y0, last point yn. Nothing's really changing apart from the fact that my diagram is now vertical rather than horizontal. y1, y2, y3, and so on. We're chopping it into n equal pieces, and each of them is given the width delta y, and delta y, of course, is 1 over n, because the length of the total interval is 1, and there are n subintervals. Okay, so what happens to these rectangles as I rotate them around the line x equals -2? So if you think about the sort of shape that they'll produce, you'll see they produce these washer shapes. Okay, so here's half of a washer being rotated around the line x equals -2. Let's think of enthusiastic there. And of course, I say we have a formula for computing the volume of a washer. This is something you can just compute offhand. I don't know if it counts as a formula, but let's go back and look at it. So see that slide again. The volume for the washer depends on two things. It depends on the big radius and the little radius and the thickness. The thickness we know is delta y. So let's add up the volumes now of all these washers. So I have n of them. So this is my approximation, right? And I have pi times the big radius squared minus the little radius squared, and both of these radii depend on where I am in this interval from 1 to 2. So I've got a particular height yi, and yi is the thing that determines the big radius and the little radius. So I've got the big radius, which is a function of yi squared, minus the little radius, which is also a function of yi squared. And then I've got to multiply by the thickness, which is delta y. Okay, so this is my approximation to this volume. And as we can see, as before, it's got the form of a Riemann sum, where I've got a function of y, but now I'm putting in yi's as the argument of that function, multiplied by delta y. And then I'm adding these up. So I know what happens in the limit. I get an integral, and I get the precise answer, whereas this was just an approximation. So let's take the limit now as n goes to infinity. So I get an integral, and the integral is over the interval that we were chopping up, which is from 1 to 2. Pi, still pi, big R and little r are now functions of y, yet to be determined. So I've got big R is a function of y, and little r is a function of y. And I replace the delta y by a dy. Okay, so all that remains to be done is to determine big R and little r in terms of y, and then I've got an integral that I can hopefully compute. So let's do that. So let's think about what big R is. So at a given height y, what is this big R? Big R is this big radius. It's the radius from x equals -2 all the way out to this red curve at height y. And I know how far this red curve is from the y-axis. It's just its x-coordinate there. So what I'll do is I'll figure out the x-coordinate of this red curve and then add that distance onto 2, and that's going to give me the big radius. So it's 2 plus whatever x is in terms of y. And what is x in terms of y on this red curve? Well, if y equals x cubed plus 1, then x is the cube root of y minus 1. So this is it's the cube root of y minus 1, and then I still have to add on the 2 to take count of this distance. And the little radius is no harder, in fact it's a little easier. Little radius is again the distance from the blue axis, x equals -2, to the y-axis, and then along to this green curve. So it's 2 plus x on the green curve as a function of y, but the green curve is just y equals x plus 1. So x as a function of y on the green curve is x equals y minus 1. So this is 2 plus y minus 1, which is 1 plus y. So then I can take these formulae and drop them in to my integral. And then, if I'm lucky, and I think I am in this situation, it's an integral that I can compute. But this podcast isn't really about computing the integral. It's about getting to that point where you have an integral to compute. So, of course, this isn't the end of the story. I've been trying to convince you that ideas, especially pictorial ideas, are easier to remember than formulae. But, of course, you don't learn mathematics just by watching it done. You learn mathematics by doing it. I like to say that when you come to university, you're doing mathematics, you're not learning mathematics, and there's a difference. So the way to get good at doing volumes of revolution, as indeed with any A-level topic, is through practice. So I urge you to go away and do some examples and try to do it with the formula sheet out of sight.